Natural physics is a concept astrophysicist Leroy Larry developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as Leroy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings, everyone. I'm Leroy Larry, and welcome to the Natural Physics Experience, live from Costa Rica. Happy and safe Juneteenth Day to you and your families. Joining me today is August Wogemuth from Edmonton, Alberta, Canada. Hey, August. Can you hear me?
Yep.
Okay. Now, August, I understand that you got hit by a baseball and it almost broke your arm, right?
Yeah.
And from what I'm told, that's not the first time that you've
It
gotten
the
hit.
exact same spot.
Yeah, that's dangerous. That's why batters wear helmets, huh? Because the pitches could really do some damage if it hits you in the head. But your arm was not broken though, correct?
Yeah.
But it must have seriously hurt.
It was hurting like crazy.
What was the injury?
A bruise.
A bruise, huh? And what part of your arm?
Right on the bone.
Right on the bone.
And it was a fast pitcher too.
On your forearm. What did you say?
And it was a fast pitcher too.
It was a fastball, huh? Not a curve or a...
Not like that, but like full on.
Whoa. Whoa.
And he also had lots of power.
Wow. Okay, well, you know what we're going to do? We're going to use physics to calculate what the acceleration of that ball was going at if it would have broken your forearm, okay?
Yeah.
When a ball is pitched, here it shows the flight going from the pitcher to the batter. Okay, August, so when the baseball is pitched to you, it's on its way to you, what's the one force of nature that we know is acting upon it?
Gravity.
Gravity. So in this diagram, that shows the force of gravity pulling down on the baseball. And that's the same as the weight of the baseball, right? Do you remember what the equation is for weight, August? Weight is W is equal to what?
Mass times gravity.
Excellent, August. Mass times gravity. So the force of gravity that's pulling down on this baseball is equal to its mass times gravity. Okay, excellent. The main thing that's going on here is the force of gravity and actually the force that the pitcher gave the ball when the ball was pitched. Now, do you remember the equation for force? F is equal to what, August?
Mass times acceleration.
Excellent, August. Excellent. So what we're going to do, we're going to find out what that acceleration had to be if the ball would have broken your arm, which we're so glad it didn't. So once again, the main forces we got is the force of gravity acting on the ball and the force that the pitcher gave the ball when the ball was pitched, okay? All right. So what I did, August, I looked up I looked up about how much force would it take to break a bone from from a baseball. So let's read this. It says about 4,000 newtons of force. It takes about 4,000 newtons of force to break the typical human femur, to break your bone. So 4,000 newtons. So we have the value for the force that baseball would have had to apply to your arm to break your arm. Now, when you play baseball, it's a hard ball. It's not a softball, right? It's a hard ball. You know, I never got a chance to play hardball, August. The only baseball I ever played when I was growing up was softball. I never got to play hardball. Okay, so it says here, a standard baseball weighs between 5 and 5.25 ounces, which is 142 to 149 grams. Okay, and this range is established by the regulations of Major League Baseball. All right, so we got the mass of a typical baseball. And it says, let's round it off to 150 grams, okay? It says 142 to 149. Let's just say 150 grams, okay? Is that okay?
Yep.
Okay. Now we need to convert that to kilograms, right? Because we're working in the meter, kilogram, second system. So
150 divided by 1,000.
yes,
0.25. 0.15.
0.15.
Yep.
Okay, so 150 grams is equivalent to 0.15 kilograms, okay? So now we have the mass of the baseball in kilograms. So now hold on to that number, 0.15 kilograms. Let's go back to this. The force is 4,000 newtons. So August, with your calculator, what number do you think you're going to divide by the other number? What do you think? To get the acceleration, it's going to be the force divided by the mass. So what are we going to do?
4,000
Okay.
divided by 0.15.
Okay, do that.
Wow!
What'd you get?
26,666.6.
Okay. Okay.
Sixes.
And August, because we are in the meter kilogram second system, if the force is in newtons and the mass is in kilograms, then the acceleration is going to be meters per second squared. So August, what that means then is if your arm would have gotten broken by the baseball would have had to have been traveling at an acceleration of the number you read, meters per second squared. And what that means is that for every second that ball was going from the pitcher to you, its velocity increased. That's the acceleration that ball would have had to travel at to break your arm. Unfortunately, it did not break your arm, so it wasn't traveling at that acceleration, okay?
Okay.
All right. All right. So now let's get back to your, do you have any questions, first of all? Okay. All right. Now let's get back to your Northern Constellation mission to Saturn's largest moon, Titan. Okay. All right. And as we already concluded, the trajectory that you're going to use to get your rockets from Earth to Titan is going to take advantage of the gravitational field of Jupiter to help your rocket get from Earth to Saturn and then to Titan. All right. So we got to look at what natural force of nature, August? What's the natural force that we have to deal with in getting your rocket from Earth?
Gravity.
Gravity, okay. Now, last time we talked about how there's a force between planets and between the sun and a planet. And it's gravity. It's the gravitational force. The same force of gravity that pulls you down to the Earth also keeps the planets orbiting around the sun, the force of gravity. And the physics equation for that is force is equal to, it's called the gravitational constant. It's a number that always stays the same. This is the mass of the sun. This is the mass of the Earth. And r squared, that's the distance between the sun and the Earth. So to calculate the force that is the force of gravity that keeps the Earth orbiting around the sun, this is the physics equation that's used. We're going to find out when your rocket passes by Jupiter, we're going to look at the force that Jupiter is going to be applying on your rocket as it goes by Jupiter to get that gravity assist. This was from last week where we showed how this is Jupiter and how Jupiter's gravitational field can be used to propel your rocket to Saturn, okay? So what we're going to do now, August, we're going to use that physics equation to find out what's the gravitational force that Jupiter, once your spacecraft gets to Jupiter and then gives it a gravity assist towards Saturn, we're going to find out what that force is that Jupiter is going to give your rocket, okay, to propel it towards Saturn. Just for comparison, August, do you remember this diagram that I showed you a while ago that compares the gravity on the different planets in our solar system to Earth, right? If Earth is 100, is the number 100, then, for example, the gravity on the moon is 16.6, a lot less than 100, right?
Yeah.
Okay. Now it says that the gravity on Jupiter is 236.4. Earth is 100. Jupiter is 236.4, which is less or bigger than the Earth, August. 236.4 compared to 100. Which one is bigger?
Jupiter.
Jupiter. Now, it says Saturn is 106.4. So, is Saturn's gravitational field bigger or smaller than Earth's? If Earth is 100 and Saturn is 106.4, which one is bigger?
Saturn's.
What?
Saturn's.
Okay. And now, last but not least, let's look at Titan's gravitational field. Titan's gravitational field is 11.9. So, it's the largest moon of Saturn. So let me ask you this, August. Which gravitational field is bigger? Our moon, the moon of Earth, which is 16.6, or Titan, the moon of Saturn, the largest moon of Saturn, which is 11.9?
Earth.
Earth. Okay, here's the same diagram, right? You have the Earth and a satellite, but instead, let's say this is Jupiter and your satellite and your rocket. So as your rocket goes by Jupiter, it has to be going at a velocity and have a force that's greater than the force of Jupiter that's pulling on it. This distance between Jupiter and your spacecraft, the more it is, the less the force of Jupiter pulling on your rocket is. So it has a better chance of not getting captured by Jupiter's gravitational field. Okay, do you get that?
Yeah.
As your northern constellation is launched from Earth and it goes towards Jupiter to get a gravity assist from Jupiter, we saw from that physics equation that the furthest it is away from Jupiter, the less the gravitational field of Jupiter is that will capture it and not let it go on towards Saturn. The force that your rocket has to be just enough so it's not captured. The distance that it has from Jupiter has to be just enough so that it's not pulled in by Jupiter, but instead it gets projected on towards Saturn. Every time your rocket, when it gets close to Jupiter, the distance has to be just enough so that it doesn't get pulled in by Jupiter, but it gets propelled towards Saturn. And then once it gets to Saturn, same thing, August. It has to have, now let me ask you this, August. There's a difference. When your rocket gets to Jupiter, you want it to be just far enough away so that it doesn't get captured by Jupiter's gravitational field and is able to get pushed by Jupiter towards Saturn, right?
Yeah.
Now, August, when your rocket gets to Saturn, do you want it to keep going past Saturn, or do you want Saturn's gravitational field to be able to capture it and put it in orbit so that it can get to Titan? What do you think?
Put it in orbit.
That's right. So there's the difference, August. When your rocket gets to Jupiter, you want it to stay far enough away so that it doesn't get captured by Jupiter and get propelled towards Saturn. But when your rocket gets to Saturn, like right here, instead of being far enough away to keep going and get propelled by Saturn further out into space, you want it to be just the right distance so that Saturn's gravitational field will capture it and put it into orbit, right?
Yeah.
We're talking about going to Titan, outer space, mysterious, unknown. And I always talk about the mysteries here on Earth, right? That are unexplored, undiscovered. So whenever something happens that's a new discovery, I like to show you that. Okay, so Tirza sent me this article about, you remember how they discovered that teenage colossal squid that had never been seen before? Well, now another sea creature has been discovered that has never been seen before. First time ever. So I want to show you this. Explorers capture mysterious deep sea squid alive on camera for the first time. What are the odds? So this is another type of squid that has never ever been seen before alive, ever, August. So I'm going to scroll down. Okay, and let's just read this. The Gnatus antarcticus squid, a mysterious squid found only in the frigid waters around Antarctica, was caught on camera for the first time on Christmas Day by the Schmidt Ocean Institute. The footage was caught by a deep sea vessel known as Sebastian. The vessel dropped 7,000 feet through the ocean on Christmas morning, stumbling upon a deep sea squid species. So this vessel found this squid 7,000 feet below the ocean. So let's play the video.
Ooh.
Beautiful, huh? August. So that beautiful creature was found 7,000 feet below the surface of the ocean. Let's calculate how many kilometers 7,000 feet is, okay? Okay, so 7,000 feet is 2.1336 kilometers, okay? So that beautiful squid was found alive, swimming around at about 2 kilometers below the surface of the ocean. Okay?
Okay.
All right. And again, a human being cannot survive that depth without a special protective vehicle, a submarine. So amazing, again, how nature can enable this sea creature to survive at that depth, huh?
Yeah.
Okay. Do you have any questions about how we've used the force of gravity, the gravitational force, the equation, to see how the distance is very important when you want to get your rocket past Jupiter and propel it towards Saturn? And when it gets to Saturn, you want your rocket to get captured by Saturn's gravitational field.
Nope. No questions.
No questions. Okay, August. All right, then, everybody. Tune in next week. Same fat time, same fat channel.